In section 4.1, we talked about inner product and we actually defined angles and lengths using it. In section 4.1.2, we'll be talking about orthogonal complement. That's going to be important when we start looking at projections. So definition 4.1.4, let V be an inner product space, let W be a subspace of V. The orthogonal complement W perp of W is, so it's going to be the set of all elements in V that are perpendicular to everything in W. So for all W in W, VW gives you 0. All right, so W perp contains the elements of V perpendicular to every single vector of W. So I'll call it W perp. So this one, perp as in perpendicular. All right, consider V equals R3 with the usual dot product. Let W be the line, X, Y, Z equals minus 1, 2, 3, T for T and R. Find W perp using geometry. All right, so we have a line. It contains the origin, and then it's parallel to the vector minus 1, 2, 3. We're in R3, so our intuition is pretty good. If I look at everything perpendicular, I'm going to get a plane. So everything here is perpendicular to minus 1, 2, 3. So that plane it has a normal vector, minus 1, 2, 3, and it contains the point 0, 0, 0. And so the plane will have equation, sorry, minus 1, so minus x plus 2y plus 3z. And then if I plug in 0, I'll get 0. So minus x plus 2y plus 3z equals 0. In fact, we had questions like this in linear 1, find the plane containing all blah, 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 blah. All right. Proposition 4.1.3, let V be in an inner product space and assume that W is the span of all of these. So in our case, that we would need just a single one. V is in W perp if and only if. You don't need to check that V is perpendicular to all of this. You can only check these generators and that would be enough. So I'm going to check that V.W1 is 0, that V.W2 is 0, and so on up to VWM. This result will be proven in a worksheet or an assignment. All right, it's not so hard. Example 4.1.7. So let's use this to algebraically find a orthogonal complement. So consider P3, polynomials of degree 3 or less, with the inner product. So integral from minus 1 to 1, P of x comes Q of x. I'm going to take W to be the span of 1 of x. You can think of it almost as P1 sitting inside P3. So find conditions on P of x that ensures that P of x is in W perp. All right, so I need to check that P of x and 1 are orthogonal, and P of x and x are orthogonal. So P and 1, that's the integral from minus 1 to 1 of P, so of a plus px plus cx squared plus dx cubed dx. And so you would get ax plus bx squared on 2 plus cx cubed on 3 plus dx4 on 4 from minus 1 to 1. And so I got a plus b on 2 plus c on 3 plus d on 4 minus minus a plus b on 2 minus c on 3 plus d on 4. So some of the terms cancel, some add up. So these cancel and I get 2a plus 2c on 3, and that must be 0. All right, so that's the first condition. We checked that P was perpendicular to the first generator. Let's do the second one. So that would mean that the integral from 1 to 1 of a plus bx plus cx squared plus dx cubed times x dx is 0. I actually computed it ahead of time to save a bit of time. So I got 2b on 3 plus 2d on 5. That must be 0 as well. Okay, so I need this to be 0. I need that to be 0. Hence, we need 2a plus 2c on 3, 0. And we need 2b on 3 plus 2d on 5 equals 0. And that's it.